We have the expression for the distribution function, which is given by f equals to 4 pi m by 2 pi kt whole to the power 3 by 2 c square e to the power minus mc square by 2 kt. And if we plot a graph of f versus c, then it will look like this. And we have discussed that this region, when the f is increasing before it attains a maximum, this region is dominant for this c square term, whereas this region where it is decaying, and it is decaying exponentially. So it's decaying exponentially due to this term mc square by 2 kt, due to 2 kt. And for this region, from 0 to up to this value, it is increasing quadratically, means as a square of c due to c square. Okay, that's why quadratically. Okay, so between all these values of c, over here f is maximum. And if you remember, f was dnc by n, so it will also be maximum. It means that n for a particular system is constant, therefore dnc has to be maximum for this particular value of velocity, which is written as cm, which is called, this velocity is called most probable velocity, for which the distribution function is maximum, or you can say the number of molecules is maximum. It means that in a system you will find that most number of molecules are moving with this velocity. That's why it's called most probable velocity. Okay, so the maximum number of molecules will possess this velocity, at which the distribution function becomes maximum, and this velocity is called most probable velocity. Okay, now if I draw the curve again, okay, so now suppose at a distance c from the origin, we take a thin strip, okay, of thickness dc. Its thickness is dc, and over here at c, the corresponding value of the distribution function is suppose f. Okay, therefore what is the area of the shaded region? Area of the strip or the shaded region is f dc. Okay, so area of this shaded region is f dc, and if you remember, f dc was dnc by n. Okay, so it means that, so fdc represents the fraction of total number of molecules with velocities lying between c and c plus dc. Okay, so this fdc represent the fraction of total number of molecules. So this is the fraction, okay, fraction of total number of molecules n with velocities lying between c and c plus dc. We know that these DNC number of molecules are moving with velocity lying in the range c and c plus dc. Okay, and DNC by n is the fraction of total number of molecules. Okay, and DNC by n is again equals to FDC. So from the curve, this strip, if we take a strip like this of thickness DC at a distance c from the origin, then it will give us the fraction of total number of molecules with velocities lying between c and c plus dc. And if we multiply FDC by total number of molecules, we will get DNC, that is the number of molecules which are moving with velocity lying between c and c plus dc. Thus, from this distribution curve, we can find, if we take various strips at various velocities, suppose over here we also take a similar strip like this, and if we can find the area of this shaded region, this green region, then we can tell how many molecules are moving with this particular velocity, suppose c prime. Okay, so we can say from this, thus from the distribution curve we can find how many molecules, suppose this is d and c prime, number of molecules are moving with the c prime velocity. That's why it is called distribution curve, means you can find how many molecules are moving with different velocities. Okay, or how the velocity is distributed among the molecules. So very few molecules are moving with very low velocity. Again, very few molecules are moving with very large velocities. Okay, most of the molecules will have their velocity lying in a moderate range, and at the most probable velocity over here you will find that most number of molecules will move with that particular velocity Cm, which is called most probable velocity.